Hello and welcome everybody. Today we are actually going to change the gear a little and we are going to look into something which is one of the fundamental aspects of constructing quantum field theory and so to say the particle physics that we are actually going to look into, which is to construct the Lagrangian. And we have already discussed the relativistic quantum mechanics, the observables and measurables like the cross sections and decay width, and we have taken the principle of abiding by the rules of special relativity and so on. But today we are going to discuss the concept of Lagrangian and the corresponding equation of motion. So let us get started. So the first thing that we would like to ask is, rather we are going to point out to one of these interesting features which is called the Fermat's principle, which is actually, if you think of the path which is taken by the light between 2 points A and B, and suppose it passes through air, glass and air, then the question is, what is the path that it actually takes? And it turns out that it is interesting that instead of taking the shortest path, it actually takes the path or traverses the path which actually takes the least time. Okay? And this is what gives you the Snell's law. Now, if I ask you that why the light is in such hurry, why it has to traverse the path which has the least time. So, where exactly the answer is lying? The answer is actually lying in something called the variational principle or the principle of least action, on which the whole Lagrangian principle is actually based upon. So, this brings us to the concept of Lagrangian or Hamiltonian. Now, classically you are quite familiar to this concept, I am sure. You know that from Lagrangian we can find the equation of motion. So, suppose a ball rolling down a inclined plane. If you have to sort of write the equation of motion, you can very well do balancing the forces which are instantaneously acting on that particular ball, etc., etc. But it is way easier that if you can construct the corresponding Lagrangian and then using Euler-Lagrange's equation of motion, you can find that equation of motion for the ball. That will give you the same answer. And the point is, it is a very generic principle which not only acts for the ball rolling down the inclined plane, but as I just said, that it also acts equally for light traversing, passing through different mediums and so on. But there is another very important aspect of having this Lagrangian formalism, which is actually the fact that this not only describes the motion for the classical particle for classical physics, but it also does the job in a quantum friendly way. We can easily generalize the Lagrangian formalism to quantum mechanical cases, and particularly the ones that we are interested in. Okay, so before going into those things, let us quickly look into the fact, first of all, that energy which is equal to kinetic energy plus potential energy is actually constant of motion, but the balance may change. How much is the kinetic energy, how much is the potential energy? Think of the ball falling from a height and coming to the ground. We always know that here the potential energy is sort of more, where when it is coming down the kinetic energy picks up and the potential energy is reduced, right. So, what we can do, that we can define the average of the kinetic energy, and let us call it T bar, which is 1 by tau integral of 0 to tau half of mx dot square integral of dt within the time interval of 0 to tau. Similarly, we can also define the average of the potential energy, which is simply 1 by tau integral of v dt from 0 to t. And so, therefore, the total energy is equal to E bar, which is T bar plus V bar. However, the T bar and V bar, this actually may change as the particle actually moves through this trajectory, right. Now, if you have this T bar which is defined as 1 by tau 0 to tau m half m x dot square dt, we can find the functional derivative of this T bar is a functional, because what we are going to do, that we are going to take a derivative with respect to the function x, which is in turn a function of time, right. So, the derivative will be a functional derivative which we call del T bar del xt. Now, if you do calculate this functional derivative, it turns out to be something like minus 1 by tau mx double dot. Okay. This is not very difficult, but it requires a bit of attention how you can do this exercise. Roughly saying that if you take d dt, this is going to be half of m 2 x dot t, and then therefore once you apply the d dt on top of that, it is going to give you m x double dot. Similarly, if we take the functional derivative of v bar, the average potential energy, del v bar del x t, that will turn out to be 1 by tau dv dx. Okay. Now, let us get back to the Newton's law, which basically says mx double dot is equal to minus dv dx. Now, if we put those expressions of the functional derivatives of the average kinetic energy and potential energy, so this relation basically turns into del v bar del x equal to del t bar del x. Okay. So, this basically means that if you slightly deviate from the classical trajectory, both the average kinetic energy and potential energy will increase by the same amount, right. So, this is the vision that you can actually develop from this exercise. Or in turn, you can actually say that the del x t of t bar minus v bar, that is actually equal to 0. So, the difference between the average kinetic energy and the potential energy is actually stationary about a classical trajectory. So, this is a very important statement, and that is what gives rise to the fact that so this is the equation of motion. This is what follows from Newton's law, right, and this basically says the difference between the average kinetic energy and potential energy should be the same. So, this gives rise to the definition of the Lagrangian, which is like t minus v, and then you can actually construct what we call the action, and which is the integral over time for a Lagrangian. Okay. So, this is actually integral of L dt over time between the interval 0 to tau. Okay. So, therefore, we can also see that if this is the equation of motion like del x t of t minus v equal to 0, and once we construct the Lagrangian s equal to integral of 0 to tau L dt. So, therefore, it basically means that the equation of motion follows this principle of least action, which is del s del x t is equal to 0, and this is what goes by the name of Hamilton's principle of least action. I am sure you are familiar with, but it is good to remind ourselves that where exactly the concept of Lagrangian came from and how exactly the equation of motion is obtained from this Hamilton's principle of least action. So, if you consider that Lagrangian is a function of x and x dot, which is mostly for all the particles that we actually see around, then what is this del x, del s, del x, the derivative that has to be equated to 0 to obey the principle of least action. So, this you can calculate, and this you can do take a derivative with respect to x with del x u del x t, and then this is del L del x dot del x dot del x t, and then you can say that this del x u del x t, this quantity is a delta function which is delta of u minus t, where this del x dot del x t, this is nothing but the ddt of the delta function u minus t, and then you can do an integration by parts to show that what you are left with eventually, that del s del x t equates to del L del x t and ddt of del L del x dot. Okay. So, this is a matter of calculation. So, you can go by this calculation neatly and rigorously, which leads you to this fact. So, the principle of least action, which says that the action must be stationary, del s del x t equal to 0, this leads to this relation that del L del x t minus ddt of del L del x dot t must be equal to 0, and this is what we call the Euler-Lagrange's equation. So, this is a very celebrated one, and I am sure you have many experiences of seeing that if you just follow the Newton's law and so on and so forth, the equation of motion that you can actually find for a classical particle, the same you can obtain by writing a Lagrangian and finding the Euler-Lagrange's equation of motion. However, for our purpose, we would like to identify particles and their interactions, right. So, it is not really the classical physics, but rather we are interested in the quantum realm, and we also established the usual quantum mechanics does not work anymore. So, it has died after we have taken the theory of relativity also in account and following E square equal to p square plus m square, because it not only provides you negative energy, negative momentum solutions which we envisaged as anti-particles, but at the same time we do not have a a consistent description of a single particle probability density or probability current density. So, therefore, we really have to give it up on the construct of non-relativistic quantum mechanics and rather focus on something called the quantum field theory. So, therefore, we will be interested in writing the Lagrangian involving fields. And once we quantize the fields, what is the quantization conditions that I will tell you, those fields actually can be assigned particle nature. So, this is precisely the procedure which we will follow. So, therefore, you can say that we can always write this Lagrangian in terms of this Lagrangian density, which is this curly L, if you see, integral of dx, or in a sense then the action will be this integral of dx dt with this curly L. And this Lagrangian density is now the function of the fields, right. And let us take a simple example. This fields can be any fields. It can be a scalar field, it can be a fermionic field which satisfies Dirac equation, or it can be a vector boson field, okay, or it can be a tensor field. You can do it for anything, but for the time being, just for the sake of simplicity and notational simplicity, let us assume that it is a function of the scalar field phi and its derivative. So, the x and x dot, which the Lagrangian was a function of, has now been changed appropriately by the field itself and its derivative del mu phi. Okay? So, this is essentially the change that we actually do from the classical Lagrangian to the field theoretic description. Okay. So, therefore, you can also say that the Lagrangian is nothing but d4x of this L phi del mu phi. And phi is a scalar field which is a number which we talked about. It can be a real number or a complex number depending on what kind of field that you want to describe it with, and so on and so forth. Now, the question that we would like to ask, that we have now changed the Lagrangian from the classical, which is a function of x and x dot, to now be a function of phi and del mu phi. The question that we would ask, that what changes that we envisage for the Euler-Lagrange's equation of motion. The Euler-Lagrange's equation of motion for the classical case was del L del x t minus ddt of del L del x dot t. Now, you remember that the job of ddt has now been taken by del mu, right. So, we can see that this del L and the job of x t has been taken by the field phi itself. So, therefore, the first term should be del L del phi. The second term, instead of ddt we should have del mu, and instead of x dot I should also have a del mu phi. Okay? And you nicely observe that this del mu index is sitting actually beneath, right, and del L del of del mu phi, उसमें mu और एक नीचे है, मतलब ऊपर eventually है. So, this mu is contracted. So, the mu index is actually summed over. It is a dummy index. It's a repeated and summed over. So, therefore, what it does, so if you have to write now the equation of motion for for this Lagrangian, which is a function of phi and del mu phi, the equation of motion turns into something like this. Okay? I hope it is understandable, but please convince yourself by this analogy. Okay? Now, let us consider a simple Lagrangian which I am writing. So, which is for a real scalar field, and I am saying that this Lagrangian is half of del mu phi whole square minus half of m square phi squared. So, these are the terms that I have written. Now, what this del mu phi whole square this means? This basically means that this term is basically del mu phi del mu phi. Okay. So, once again the mu is repeated and contracted, it is a dummy index. Suppose if this is the Lagrangian, what is the corresponding equation of motion? So, this is the example of a Lagrangian which we just said, it is a function of phi and the derivative of those fields like del mu phi. So, this is the kinetic piece, the first term, and the second term is usually written as a mass term. Now, the first question is that what is the equation of motion? Suppose if I do del L del phi, what that will be? This is very trivial. You can simply take the derivative and it will be simply minus m square phi. Now, what will happen if you take del L of del mu phi? Now, it is very clear that if you do that, this is going to be, because del L of del mu phi, so this is going to be simply del mu phi, right. So, now let us write the full Euler-Lagrange's equation of motion. What exactly it is going to be? It is going to be del L del phi, which is minus m square phi, and del mu of del L of del mu phi, this is going to be minus del mu of del mu phi. Now, you remember del mu is what we call the box operator. So, this equation simply becomes box plus m square phi equal to 0. Now, does this equation look something familiar to you? I am sure you remember that this is the first non-relativistic equation that we actually constructed. This is what is called the Klein-Gordon equation. So, the first thing that we did was actually to construct therefore a Lagrangian which leads to the case of Klein-Gordon equation, right. So, the equation of motion basically will lead you to Klein-Gordon equation. So, this is an interesting point. Now, the other thing that we would like to observe later, that each of this Lagrangian carries certain symmetries. You know, there is a certain kind of transformations on phi that you do which keeps this Lagrangian invariant, and that has some non-trivial consequences, and this is precisely what we are going to talk about. But for the time being, it is good enough for us to observe that this is the Lagrangian for one of these equations, relativistic equations that we actually obtained, and that is what is the case of Klein-Gordon equation. So, therefore, the Lagrangian for scalar fields you may say can be written in this particular way with the kinetic and the mass terms. And of course, you can dress it up further. I will take up one more example later, but now let us ask this question, that why this Lagrangian formalism is useful for us, but not something like Newton's law. We could not extend the Newton's law to do our job. The answer simply lies, I mean, this is quite obvious to you, that this is because we are doing quantum physics. Even if you do not say mechanics, it is a quantum physics. So, the motion of any particle for going from a point A to point B involves basically all possible paths, and quantum mechanically we know that everything has to be summed up, and it turns out that some of those possibilities, you know, these phases that are there for each of these cases, and for most of them when they add, these different phases leads to cancellation, giving you only a stationary and non-zero contribution, and that is the classical route that the particle takes. If you think it in terms of wave functions, then you can say that the particle actually has a wave function which is a function of e to the power I s by h cross, where s is integral of L dt, which is the action. So, the stationary phase basically equates to the stationary action, or it in turn indicates to the variational principle that we talked about. So, the action is stationary, then the classical path which minimizes the action is the only one that is observed, and the other ones are actually cancelled. However, if you are thinking of Newton's law, that actually gives the same classical path, but it does not allow you the generalization to the quantum physics, or which is to kind of consider all possible paths through which actually the particle can move. So, therefore, to formulate quantum field theory, which we are going to do, we need to start with the Lagrangian picture which we are doing. So, suppose now I would like to generalize the exercise which I did just before to write a Lagrangian for a complex scalar field. Now, a complex scalar field, that is something that you all know. So, it will have two real degrees of freedom. So, I can define my capital phi to be phi 1 plus I phi 2. So, how do I define the corresponding conjugate? The complex conjugate will be phi 1 minus I phi 2. So, this is a Lagrangian which basically involves 2 degrees of freedom, right, 2 real degrees of freedom in terms of phi 1 and phi 2, or you can say, I can also say that phi and phi star are my 2 degrees of freedom with respect to which I would like to write. So, therefore, once again what we can do, that we can first write the kinetic term. How do I write the kinetic term? This is actually del mu phi star, this is del mu phi, and once again you see that this is nicely Lorentz covariant, and this also gives you the real numbers at the end of the day, because it involves both phi star and phi. And then what will be the mass term in this particular case? I should write it like phi star minus m square phi star phi, and I can also write an interaction term of the order of phi star phi whole square, which is proportional to some constant g, which gives you some self interactions about them, right. So, this is one possible way of putting up the Lagrangian for a complex scalar field. Now, this will be a homework exercise for you to find the equation of motion. So, this is a homework exercise which you should do, that find equation of motion for this particular case using Euler-Lagrange's equation. Now, we come to a $1,000,000 question, which is that we have talked at length about the Dirac equation and the kind of particles which solves Dirac equation. What exactly are those kind of particles? We have said that those are fermions, although when we talk about their spins there is a bit of an issue, and so on and so forth. So, we talked about the Dirac equation at length, and we have talked detailed about its possible manifestation of the solution of the Dirac equation. The question is, what is the Lagrangian that will give you the Dirac equation as an artifact of equation of motion? I mean, when you pass it through this prescription of Euler-Lagrange's equation of motion, what will be the Lagrangian that is precisely what is called the Dirac Lagrangian that will give you the Dirac equation? So, let us try to construct the Dirac equation and see if it is correct. So, suppose you remember the Dirac equation, I gamma mu del mu minus m psi equal to 0. So, that is my goal, that is precisely where I have to reach after doing this exercise of going through the equation of motion, the way that I actually obtain the Klein-Gordon equation from the Lagrangian that I constructed. So, similarly I would like to do the same for the Dirac equation. So, the way that we can do it is to write it psi bar I gamma mu del mu psi minus m psi bar psi. And once again you remember, gamma mu is my gamma matrices, psi is my Dirac spinors, psi bar is what you call the conjugate Dirac spinor, which is defined by psi dagger gamma 0. Now, the question is, how do I get the Dirac equation out of the Dirac Lagrangian? The answer is simple. Now, if you have to write the Euler-Lagrange's equation corresponding to this fermionic fields, we should write it like del L d del psi minus del mu of del L d del of del mu psi equal to 0, right. So, this is precisely what we need to do. And suppose now I have a definite L d Dirac Lagrangian that I have written here for you, and let us check whether this Lagrangian utilizing this you can find the equation of motion. So, let us do this first exercise of finding del L d del psi. क्या होगा बोलो, del L d del psi, देखो this first term is actually a function of del mu psi and this has a psi bar. So, therefore, this will not contribute to del L del psi. So, del L del psi will give you something like minus m psi bar. correct? And what will be del L D del of del mu psi? That will simply give you psi bar I gamma mu. अभी इसमें बैठा देते हैं. If you put these two solutions above into the Euler-Lagrange's equation of motion, इसमें बैठा देने से क्या आएगा? माइनस psi bar m minus del mu of I psi bar gamma mu is equal to 0, correct? Now you can also write psi bar as psi dagger gamma 0 following the definition, and same here inside the del mu. Now what we are going to do, that we are going to take a Hermitian conjugate. Hermitian conjugate के मतलब क्या है? If you have A, I am going to take A dagger, complex conjugate का transpose. So that's usually the meaning of taking a Hermitian conjugate. So if I take a Hermitian conjugate of this psi dagger gamma 0, क्या होगा? It's a dagger, right? So AB whole dagger becomes B dagger and A dagger. So this will become gamma 0 dagger, psi dagger, ka dagger will become psi, and so on. And here I have actually, when I take the dagger, because I am also taking the complex conjugate, so this minus of del mu I psi dagger gamma 0 gamma mu, thus becomes I gamma mu dagger psi 0 dagger. So this will come first, this will come second, this will come third. So this is gamma mu dagger, gamma 0 dagger and psi. Now you remember that we also talked about these properties of the gamma matrices, that the gamma 0 dagger is gamma 0, gamma k dagger is minus gamma k, and there is an anti-commutation of gamma k and gamma 0 when k is not equal to 0, which is gamma k gamma 0 is minus gamma 0 gamma k. So with this, what you can see that I have basically gamma 0 dagger will become gamma 0 and psi m remains psi m, and within the bracket this is I gamma 0 gamma mu. I have flipped the position of gamma 0 and gamma mu. Gamma 0 gamma mu psi is equal to 0. Now what I am going to do, that I am going to multiply this particular equation from the left with a gamma 0 and utilize the fact that gamma 0 square equal to 1. तो क्या आएगा देखो, if I multiply this with the gamma 0 and this thing, this will simply become minus m psi, the first term, gamma 0 square is equal to 1, and the second term क्या होगा? See, del mu will only act on the psi which has a spatial function, I mean which is a function of x and t, right? I mean it will not definitely act on gamma 0 and gamma mu, which doesn't have any special dependencies. So this term becomes I gamma mu del mu psi with gamma 0 square once again becoming 1. Now what this equation is? If you look closely, if you write the second term as the first term, this is I gamma mu del mu minus m psi equal to 0, and this is precisely the Dirac equation. This is precisely the Dirac equation. Lastly, you would like to ask me that why this is only, you know, we wrote the Euler-Lagrange's equation in terms of del L D del psi. Now you can ask that in the Lagrangian that I wrote, I also involved the conjugate Dirac spinor like psi bar. So you can argue that in principle I should get back to the Dirac equation by writing a corresponding Euler-Lagrange's equation for the adjoint spinor, like for the psi bar. I say absolutely you are right. I can write alternatively a Euler-Lagrange's equation in terms of del L D del psi bar minus del mu of del L D del of del mu psi bar. But the point is, here you can observe from the Lagrangian that del mu psi bar देखिए कोई term है ही नहीं. So therefore this second term, which is like del mu of del L D del of del mu psi bar, this term actually goes to 0. So this term, if I write it once more, this term actually goes to 0. And if you look into what is del L D del psi bar, however, this will have two terms like I gamma mu del mu psi and minus m psi. So this will be del L D del psi bar equal to 0, gives you once again back the Dirac equation. So therefore in this exercise today, we have done a very important job to write Dirac's Lagrangian. from which if you write the Euler-Lagrange's equation of motion, you obtain the Dirac equation, and that Dirac equation is this one. The first one is the kinetic term, the second term is the mass term, and this is going to be the basis of doing or extrapolate our interactions and doing a bit of quantum calculations related to the electrons, say for example, and so on and so forth. So, that is what we are going to take up later, but today we are going to finish right here, and in the next lecture we are going to talk about the symmetry principles. Okay? Thank you very much.